Okay, so it's my pleasure to introduce Dr. Pierre Haenecour. Pierre is at LPL, the Lunar and Planetary Laboratory at University of Arizona. And I'm going to give a brief introduction about him and let him do most of the talking today. It's his day. So Pierre did his bachelor's and master's from the Free University of Brussels. And then he moved to the US, where he got a second master's, his PhD at Washington University in St. Louis. And then he stayed there as a postdoc for a year. And then he came to LPL as a postdoc from 2017 to 19. And then LPL loved him so much that they just kept him. And so he started as a tenure track assistant professor at LPL. He's been there since 2019. And since 2021, he also has an additional designation. He's a visiting professor at McDonald Center for Space Sciences, right? Okay, cool. So Pierre has won a number of awards. I'm not going to go through all of them, but a couple of them that I would mention. One is that he was selected for the AAAS Science Program for Excellence in 2017. And he also won the Meteoritical Society Early Career Scientist Award in 2017. Pierre is associated with the OSIRIS-REx mission, which I'm pretty sure all of you know about. It's like one of the highlights of the University of Arizona right now. He's the lead for the Sample Analysis and Data Archiving Working Group there. He's also a member of the Sample Elements and Isotopes Analysis, the Sample Organics Analysis, and the Mineralogy and Petrography Working Groups. In terms of Pierre's research, his interest focuses on basically the building blocks of the early solar system. And he looks at the origin of life, circumstellar and interstellar dust grains and organic molecules and planetary materials. He mostly studies meteorites, micrometeorites, and even interplanetary dust particles. Super interesting. He's a geochemist and cosmochemist. He has a pretty wide range of interests. So he looks at terrestrial samples as well. So he's done like lead and zinc isotope work on Orcaean comateric lavas. And then, of course, he looks at primitive extraterrestrial samples as well. And he uses a variety of interesting in-situ ion and electron microscopy techniques. So I'm not going to talk anymore. It's all up to you here. Okay. Thanks again for coming.
Thank you so much for inviting me and for offering me to come show you some of the work that I've been doing. And I'm going to focus on something slightly different from what I've been working before. So in the talk that I've put together today was focusing on some new in-situ heating experiment that we are doing on analog materials. So still using meteorite, but looking at how grains, small dust grain, in particular, in this case, silicate dust grains and organics are affected by heating or thermal processing in different environments. Just to tag, so a lot of the work that I'm going to show you today is not just from me, it's a collaboration from both people here at the University of Arizona, the University of Toronto, at Purdue University, and then at the Argonne National Lab, as well as a collaboration with Hitachi as a high technology. As you will see, a lot of the instrument that we use for that particular talk are instrument in the Kuiper facility in the basement that are all Hitachi instruments. So when we think about thermal processing in the early solar system or in space in general, there is different type of processing. So if you think about stellar environment, so a lot of the work that I've been doing in the past was studying silicate dust in stars, so looking at circumstellar dust, but not looking in stars like in astronomy, but looking at what we call pre-solar grains, which is those small, tiny silicate grains that we actually find in meteorite that we have completely exotic composition that basically demonstrate that they form in other stars. And so what we learned from those stars is that there is both amorphous and crystalline silicate, showing that there is some processing happening, either linked to thermal processing, irradiation. We don't really understand what's happening, but it's a very high energy environment. It's a circumstellar environment. So we know that some of the amorphous dust likely didn't condense as amorphous silicates, but was actually processed through some kind of alteration. And then if we look at the astronomical observation, there is only between 10 to 20% of crystalline silicate, all the rest is amorphous material. Then if we look at other type of grains, so carbonaceous grains, so there is in stellar environment, there is not just silicate or oxide grain that form, but there's also carbon-rich grains. So there is silicon carbides or graphite that actually condense in stellar environment. And studies of those grains from meteorites have shown that they have really large abundances of noble gases, showing that they basically had implantation of noble gases into the grain, showing that they were irradiated by high energy particles. In addition to those processing in circumstellar environment, we know that those grains were exposed to both heating and ion irradiation, both in space, so in this stellar medium, so as freely floating particles, or in airless bodies, so like on asteroids, on the surface of the moon. So there is different processes that can affect the grain. So here I show you some example. We know that there is those space weather, what we call space weathering. It's basically just cosmic rays hitting the surface of asteroids or the moon, and basically affecting the really top layers of those bodies and creating those nanophase iron particles. So all those bright spots you can see on that image are tiny particle of metal, iron, nickel, metal, mostly iron, but with a little bit of nickel. So we know that there is thermal processing happening on the surface of airless bodies. In addition to thermal processing, we know that in the solar system, there is also alteration associated with water, so fluids in particular. So there is aqueous alteration, hydrothermal processing, so couple of like low temperature hydrothermal processes on the surface of asteroids. So we know there is a complex history of thermal processing or alteration on the surface of those asteroids. Now the question is, how can we untangle those processes or get information on alteration? Typically, the way we learn about alteration on asteroids is through two different sources of samples that we get. The most common that you must be the most familiar with is meteorites. Some is basically pieces of asteroids that enter the Earth's atmosphere, collected on the Earth's surface, either because someone saw it fall through the atmosphere, that's what we call a meteorite fall, or found on the surface randomly, typically in hot or cold deserts. Antarctica is a prime space for NASA to collect meteorites. And so those meteorites have provided us tremendous insight into alteration processes. The other way we can get insight into asteroids and processing in the solar system is through sample return mission. And one way that and so far we have sampled, we have sampled from 3 different sample return missions that will be available. The first one that's already returned to us is the Japanese Hayabusa 1 mission that collected samples from what we call ordinary chondrites. It's the most abundant type of meteorite, so it's a very common type of meteorite. It only collected a few milligrams of samples, so the collection mechanism didn't actually work, and so they only collected whatever entered the collector when it touched the surface, but it didn't actually collect material per se, and so it collected a very, very small amount of material. You may have heard in the news last December, the Hayabusa 2 team just returned to the Earth in Australia, sample from asteroid Ryugu. You can see a picture here. It's a CMCY-like carbonaceous asteroid. So it's a particular type of meteorite that's enriched in carbonaceous material, so in carbon. And so those samples are currently being studied. We actually have samples here in Kuiper with people working on samples in the lab right now. We don't have, I won't have much to tell you about those. There's still an embargo on any of the results from Hayabusa 2, but you should be hearing news about those samples in the coming weeks or months. And then, as you must be familiar, because it's the mission is led here at the U of A, we are currently working on getting ready for the return of the samples from asteroid Bennu, which is also a carbonaceous asteroid, potentially based on spectroscopy, remote sensing data, CI, CM-like materials, which is basically aqueously altered carbonaceous chondrites to experience alteration, both thermal processing and interaction with water. And I'm going to show you in a minute. Here you can see the capsule from Hayabusa 2, landed in Australia. You can see the first image of the sample in the collector. So there are different chambers. They collected sample from different locations on the surface of the asteroid. So you can see those different locations. A first thing that's obvious from this image, it's very dark, which makes sense. It's supposed to be a carbonaceous asteroid. So usually material from carbonaceous asteroids are very dark, material typically looking like charcoals almost, and can actually crumble it. Crumble it in your finger. Some of the initial results we have heard that they have a really hard time even preparing samples, so like making thin sections or mounting any of the sample, because by just trying to grab the particles, they actually like break, and it's very fireable. For asteroid Bennu, the tag event happened on October 20th last year. You can see here a video of how the tag event happened. So the tag SAM, the head collector, touched the surface, blow nitrogen, collected sample, and then back away. You can see after the impact, all the material flying away. The tag event works amazingly. It collected even too much samples. So as you might have seen the pictures where when they did the maneuver to extend the arm in space and look at the collector, so having the collector head actually face the camera to take pictures, we realized the particles were actually being released is because it collected so much material that the flap that was supposed to close the collector actually didn't close because it was packed with material. And so it was releasing material in space. So we basically, as soon as they saw that on the picture, they basically stowed the collector. So they put it back in the capsule and put it safe in the return capsule and then left it there. And so now, since May this year, sorry, the time seems already far away, but it's only a few months ago, the spacecraft left the orbit around Bennu and is flying back to the Earth, and is expected to come back to the Earth. It's in September 2023. So, but the reason I'm talking about those sample return missions is because a lot of the work that we are going to do on studying those samples is trying to understand their history and trying to see what can we learn in terms of the early solar system, formation of the solar system, and alteration of the history of those samples. From samples we already have, and from remote sensing, we know, for example, from Haenecour 1, we know that those samples experience alteration, so passing, but for example, they have space weathering associated with, for example, micrometeorite impacts. So they see here on some of those tiny particles, you can see there is those really nanometer scale impact on the surface of some grains, demonstrated that the material on the surface of the asteroid is impacted by soil particles that's associated with space weathering. So we know they are affected by impact, so they are affected by some kind of thermal processing associated with those impacts. And then from remote sensing of both Haenecour 2 and OREX, we know that both asteroids have signature that's consistent with both presence of phyllosilicates. So we know there is water, so there is likely evidence of aqueous saturation. And then there is evidence of potential thermal processing just based on comparison of spectral features with known thermally altered meteorites. Another event that we were not expecting on the surface of Bennu was a particle ejection event that was observed by the spacecraft. So you can see here, there's the asteroid surface, and you can see those stream of material. So they basically ejected particle while the spacecraft was orbiting the asteroid, and the modeling of those thermal events suggests that it's thermal fracturing, volatile release through dehydration of phyllosilicate, or meteorite impact that caused this ejection of particles. Whatever reason that particle ejection event happened, it basically showed that it was associated with some thermal processes, either associated with an impact or the release of thermal fracturing or release of phyllosilicates. So now I basically show you in a short amount of time that we do have evidence of both thermal processing in space, in circumstellar environment, and on the surface of asteroid. So now the question is, what can we do to try to model or try to constrain in a more quantitative way thermal processing on those in those particular events? And so what we try to do is using in-situ heating. So inside of an electron microscope, in particular here we use the transmission electron microscope, doing in-situ heating. And so we can basically watch the sample as it's being heated and getting really detailed constraint on the relationship between composition, mineralogy, microstructure in function of temperature. And so I'm going to show you two different examples of what we have been working on. The first one is trying to simulate thermal processing on asteroids, so doing both flash heating and slow heating, and seeing what's happened to both in terms of composition and mineralogy. And then the second experiment we've been doing in collaboration with Argonne National Lab is combining both heating here at the University of Arizona with ion irradiation of the material to see if the impact of ion irradiation on the sample as well. In terms of instrument, you can see here, so that's how the basic heating holder works. So you have a small heating ship with this silicon nitride film in the middle that's being heated, and the black is basically those holes. It's 30 microns holes, so we only heat very, very small particles. We want them to be as small as possible so we can look at them in a transmission electron microscope, so you can actually get information in transmission. And we did that in two different instruments. The first one was a low acceleration voltage hybrid STEM SEM. So it's basically a hybrid between a traditional SEM that you must be familiar with and a STEM. So it allows us to do both transmission and typical SEM imaging. And then we also do additional measurement or additional experiment using the Hitachi HF5000 here in the basement of Kuiper. It's a STEM TM 200 kV instrument. And then more recently, just in the past few months, we also acquire a new heating system for the Hitachi S4800 that we have in the facility here. So we'll be able, in addition to doing heating with a 200 kV with a TM, we can also do it at 30 kV on a SEM instrument. Okay, so for the first part, which is basically simulation of heating experiment, we use carbonaceous chondrites. A very famous one is the Tagish Lake meteorite. It's a meteorite fall. It's fall in Canada by Tagish Lake. So part of the meteorite actually fell in Tagish Lake. And so basically that's why it came its name. It's a very particular meteorite. It's what we call a C2 and group. The 2 is basically saying it experienced aqueous alteration, and group is because it doesn't look like any other meteorite in our collection. And if you look at that image, it's very black. It's very like charcoal. Similar to it, if you would grab it in your hand, you could actually break that whole sample by just crumble it in your hand. It's very friable. It's extremely enriched in carbon and hydrated minerals. And so it was really appropriate for us to try to investigate as an analog material for what we expect from both Rugu and Bennu, but also to try to see what happened to both hydrated minerals and organics as they were slowly heated. The way we did it is in vacuum, in the SEM itself, at temperature from room temperature up to just over 1,000 degrees. And you can do it by any step you want, and you can heat the sample for several hours. So we did different types of heating regimes. So you can see here, the first one was a flash heated. So we flash heated the sample to 800 degrees in less than 30 seconds, then put it back to room temperature, did some imaging. We did the imaging at 200 degrees. The reason for it is just because as the temperature is slightly increased, it doesn't affect the material visibly, but it's increased the electron yield. And so it basically gave us better imaging. So it allows us to get much better imaging. So all the imaging was done at 200 degrees. After some EDS, we put back the sample to 900 degrees for 30 minutes to see what's happening. Went back down to do more imaging, and then flash heated for 10 minutes at this time at 1,075 degrees. You can see here one of the sample in the silicon nitride film. So you can see here the particle with the silicon nitride film around it, and that's the heating material. You can see the EDS map. So it's basically a composite maps of nickel, iron, calcium, sulfur, silicon, magnesium, oxygen, carbon. The only thing I want you to see, it's a lot of different colors. The only thing that I want to point out is that there is both iron sulfide, there's a lot of carbonaceous material. So all the greenish colors is carbonaceous material. Carbonaceous material is mostly composed of organic matter. So, and then magnesium, magnesium, iron, and calcium-rich silicates, and then some iron nickel metal around it. Okay, so we do two different types of imaging on the live while we are heating. there is secondary electron that basically give you information on the surface of the sample. So you can see here how the surface of the sample look like. And then we can do what we call bright field and dark field imaging, which is transmitted imaging. And so you can see through the thickness of the sample. So you can see actually that image show you inside of the sample. And the contrast is based on different type of elements. And you can see here, so that those two images, both the secondary electron and dark field, ADF is for annular dark field images, is showing you before we did the heating. Then you can see that after the flash heating, you can see that the surface actually look a lot more different. It shows that there is a lot of melting happening. And we can see that even inside of the sample, there is a lot of things that happen. You see the contrast change a lot. So it clearly did affect the sample. When we went to 900 degrees, it's even worse. You can see that now you can clearly see that it actually formed those bright particles or nanoparticles inside of the sample. And I'm going to show you in a minute what those nanoparticles actually are. And you can see that they have most of the large one actually show this round shape, but some of them are clearly irradial particles. But it really showed this really melted texture with some of those particles actually even reaching the surface of the sample. And then at 1,000 degrees, it's even worse, showing you that those melted particles are even larger. So here we'll show you for a bright field images. So it's basically opposite from the dark field. So what appear really bright in the dark field is black now in the bright field, but just showing you for a comparison that those large nanoparticles are basically getting larger. So here you can see how it actually look like after the flash heating. And then if we look at the elemental composition for the 3 different steps, so I didn't show you the 1,000 degrees because it basically showed the same trend as 900 degrees. But as you can see, it's getting, the carbon signal became stronger and stronger. And what we saw is basically showing that you go from amorphous carbon, so like organic matter, or aromatic carbon, to graphitic carbon. So you basically graphitize the organic matters that's in your sample as you heat it up. If we look at sulfide, here I'm showing you in yellow sulfur matte. So all those white spots are most of them are likely iron sulfide. You can see that as you heat the sample, especially after long exposure 900 degrees, you lose most of the iron sulfide, showing that most of the iron is gone and the sulfur is basically just vaporized. It's probably just left in the vacuum. So you basically lost it from the sample. And then if we look at the iron, which is the most interesting in that aspect, you can see that between room temperature and then the flash heating, there is clear differences, but there is no already clear evidence for those nanoparticles. We can just see there is some rearranging of the iron, but then going to 900 degrees, you can clearly see that now you form those iron nanoparticles. So basically, all those bright particles that you see all around the sample is basically just iron metal that basically form. It might not be pure iron metal, because if you look at the silicon signal, you actually have silica, a significant amount of silicon in it. We couldn't quantify it yet. We are working on actually getting quantification on the silicon signal, but it's mostly just iron nickel particles. If you look in more detail at the nanoparticles, you can see that while a lot of them are showing this more circular texture, some of them clearly has a more irregular shape, showing that it's actually probably crystalline, like crystalline metals. So you actually form metal particles, not just iron nanoparticle. And then if you look at the carbonaceous material, there is this curly shape feature that you can see around that basically reflecting this graphitization. So going from forming this diffuse aromatic carbon, going into more organized sheets of graphene, so graphitic layers. And then just to show you the similar idea of showing you that those nanoparticles are all around, and they color it both for iron, nickel, and then a little bit of silicon, showing you that they are both iron nickel particles with a little bit of silicon. And it's difficult to see on this screen, but you can see that the nanoparticles are even more complicated. And so you can see in this particular one, you can actually see exolution. So there is some kind of exolution. So it's not a homogeneous decomposition. So there is a lot of complicated things happening to the sample as it's being heated. The second experiment that we did afterwards was to try to replicate a similar heading that we did using a similar sample. So it's not the same sample, exact same sample, but it's the same meteorite that was loaded on another heating chip. But you can see if you look at the before heating, so here is an image of the sample and the elemental maps, you can see it's similar, showing you that it's both iron, magnesium silicates, organic matter, and then some sulfide and iron metal. And in this case, we did a way more gradual heating, not doing any flash heating, going from 200 degrees for a long period of time to 4, 5, 600, 7, 8, and then finishing by 10, 1,000 degrees, and all for like about 20 to 20 minutes or longer. This particular time was chosen randomly. It was just to try as a first test. So just to see how gradually heating was working for us and see where the most changes actually happen. And in particular at 500 degrees, we try to leave it longer to see if we see any changing happening on the long term that we didn't expect. We didn't see any additional changes as you leave it to 500 degrees. If we compare the different steps, so I'll show you the different steps here. I'll show you all the bright field images as you go from before room temperature to 5, 6, up to 1,000 degrees. It basically shows you the same trend. So as the sample is heating to higher and higher temperature, you basically create more and more of those nanoparticles. We oriented a lot of those are in the sample accumulating in those nanoparticle, and I'm going to show you in a minute. It actually moves the iron, so it's actually melt your sample, and you can actually see the iron moving, swimming around in your sample, swimming in this matrix of carbonaceous material. Just to show you here another overview before and 600 degrees, and then going from 600 degrees to 1,000. So now you can see at 1,000 degrees, there is nanoparticle all around, and the carbonaceous matter went from being this dark, diffuse material without any features to this more like curve-like texture. And you can even see in the carbonaceous matter the trace of where the particle actually move around. So those widest areas is basically just particles that actually swim around in the carbonaceous material. In terms of composition, we see the exact same trend that we saw before. So we saw that basically the signal become stronger and stronger in carbon, especially at temperature above 600 degrees. Same for sulfides, not much happened until 700 degrees. And then after temperature above 700 degrees, you basically lose most of the sulfur. And so most of the sulfur is volatilized in the vacuum, and the iron is basically relocated in those nanoparticles. And so the iron nanoparticles are forming from both the silicates that are present and a lot of those iron sulfides. I'm going to show you a short movie. So the movie was actually acquired live at 900 degrees. So we are basically stable at 900 degrees, showing you what's happening to those iron nickel particles. The matrix around here is the carbonaceous matter. Those material is iron nickel nanoparticles, and I'm particularly showing you that one that you are going to see swim around. It's accelerated, so it was run over several minutes, and I'm going to show you in just a few seconds, but just to show you what's actually happening. And you can see that basically what's happening to the sample, it's actually melted particle swimming around in the carbonaceous matter, agglomerating together to form those larger particles. So you're literally just accumulating them, forming larger and larger iron nickel particles. And you can see also, interestingly, you can see because of the movie started just when we were reaching the 900 degrees, it basically shows you how the focus actually changed as you are heating the sample. So it's out of focus at first until we actually reach the 900 degrees. And so you can see it's basically happening everywhere. It's basically just swimming around everywhere. If we look at the actual elemental maps afterwards, you can see similar to what happened. Iron nickel particle, clearly with some silicon in it. If you look at the texture, secondary electrons, so showing you the surface, you can see that the surface show you clear morphology of like material actually melting and going away. There's like vesicle going out. There's nanoparticles that actually even reach the surface, so you can see them all around. There is exolution showing here, for example, there is a nanoparticle that basically show a clear exolution with different concentration of iron. So you can see on the elemental map, there is way more iron on this side. And so there is a lot of happening, and there is some of them, I don't remember if it's on that image, some of them have this clear heuridral shape showing that it's actually like a nice crystalline metal core. If we compare to a previous observation of carbonaceous chondrites, I'm going to briefly show you in which context in cosmochemistry we have seen those nanoparticles before. There is a few environments in which we see those nanoparticles. So the most common one is for nanophase iron, that's studied for the surface of the moon. So if you remember at the beginning of the talk, when I talk about space weathering, one of the clear things, evidence of space weathering on the surface of the moon or on the surface of asteroids, due to both micrometeorite bombardment, but also iron irradiation due to cosmic rays, is the formation of those nanoparticle, nano-iron particle that you can find on the surface of grains, on the surface of the moon. And so that's a typical environment. Space weathering is a typical way of producing those iron nickel nanoparticle, which is similar to what we have seen, for example, with the flash heating. So it's consistent with what you will expect for impact, a really quick high temperature event. Or you can imagine with also a cosmic ray particle, basically bombarding the sample, hitting it quickly, forming those particles. So it's similar to what we have seen with the first experiment of nanophase iron. We have also in carbonaceous chondrites, those iron nickel particles have been observed in a particular type of sample we call chondrules, in particular here in dusty olivine in chondrules. So chondrules are those spherical beads of glass that you can find in carbonaceous chondrite, in chondrite. So basically that's where the name chondrites or meteorite come from, because they all contain those chondrules that we know from by some kind of flash event that basically melted dust really quickly, and then that dust condensed into either a mixture of glass and silicates. And so some of those silicates here, you can see are olivine grain, show these include nanophase particle included in them as inclusion. It's basically showing olivine grain with those iron nanoparticles. And then the last example that we have is what we refer to as gems grain, which is glass with embedded metal and sulfide. Those are actually found in cometary materials. It's found in material that we think come from comets, in particular interplanetary dust particles. They show those really large area. I mean, for us, it's very large, it's probably not large for you. It's several hundred nanometers inside of a glassy matrix, basically composition similar to like a magnesium silicate, but amorphous magnesium silicate with those embedded iron nickel particles and some sulfides. There's basically the three main environments where we have been observing those iron nickel nanoparticles so far. Okay, so now I wanted to switch to the second type of experiment that we've been doing. We're trying to not just looking at thermal metamorphism by just heating, but combining it with iron irradiation. So what we did in this case, instead of using a meteorite to try to constrain it even better, is just using standard material. So here we just use silicate, San Carlos olivine. You must all be familiar with San Carlos olivine. Very similar to what we would expect, for example, for a presolar silicate. Olivine is a very typical presolar silicate. We basically grinded San Carlos olivine, then loaded it on the heating chips here, so it's basically small enough that it can actually be imaged in a TM without any issue. And then we went to Argonne National Lab using the Hitachi 9300 kV TM that's connected to a xenon and helium ion beamline, so you can irradiate your sample both either with xenon or with helium. You can choose by just being, there is this line is at 30 degrees angle going through the ion electron column. So basically you can image your sample as it's being irradiated by xenon or helium ion, and it's extremely high vacuum. So you are basically in a vacuum environment. Okay. And then we carry out, similarly to the first experiment I show you, we did all the heating here at the U of A in the Kuiper facility using the 30 kV SU9000 STEM SEM. And in this case, we did flash heating with a longer flash heating going to 1,000 degrees, but for a period of about 5 minutes, and then imaging again at 200 degrees temperature, combining both EDS and then imaging. Okay, so I'm going to show you two different irradiation we did. So we did helium irradiation in implantation using 20 kV helium ion, and then xenon irradiation at much higher energy to try to see what's happening at different energy with different type of ion. And then they both follow the same heating regimen to see if we see any difference between the type of ion that we are using based on compared to the same heating experiment. Okay, so here I'm going to show you the transmission electron microscope image of the olivine, the San Carlos olivine before the heating. You can see, if you're not familiar with TM imaging, you can see the lattice fringes here on the olivine, basically showing here that it's a crystalline olivine. So it's a typical San Carlos olivine. There is nothing wrong. There is nothing wrong in terms of the crystallinity of that particular olivine grain. So it's just crystalline olivine, which is all we cared about at that stage. And then you see just after the xenon irradiation, so high temperature irradiation, you basically lost all the crystallinity in the sample, and so basically amorphized completely the sample. So we went from crystalline San Carlos olivine to amorphous silicate. In terms of the helium irradiation, what we see is that we actually implanted helium ion into the sample. You can see here the small bubble inside of the sample all around on the edge. So it's actually trapped into the olivine grain. So it was actually trapped inside. You can see it on the edge where it's thin enough to images. So it's full of those helium bubbles. And then I'm showing you here, I think it's a short movie, showing you what's happening to it as it's being heated to the 1,000 degrees. It's basically showing you the different stage. The focus is changing because we are increasing the temperature. So you're going from 200 degrees to 1,000. So you can see basically all those nanoparticles just appeared as you were heating the sample really quickly. If we look at what happened to the actual edge where there is those trapped bubbles, you can see here it's relatively dark, but it's basically showing you trapped helium on the edge of the sample. And then after the heating, you basically release all those bubbles so you can actually physically see the holes in the surface of the sample. It's secondary electron image, so showing you the surface of the sample, showing that you basically release all the helium and then form nanoparticle all around. So if you look in the transmission, the bright field image, you can see that in addition to changing the structure inside of the sample, so you don't have the helium trapped inside of it anymore, you actually form iron nickel nanoparticle all around. Here on the surface, you can see again this texture showing you to basically release all the helium, showing you those open basically vesicles that basically were release all the helium that was trapped. And then even formation of those iron nickel nanoparticle on the surface of the sample. So it's actually a 3D particle that actually form on the surface of this olivine, what used to be a olivine grain. Showing you in a more larger field, showing you what happened to the sample. It's basically a lot of bubbles all around it, and then released afterwards. You can see that now it's mostly composed of those iron nickel particles. They are literally everywhere after heating at 1,000 degrees for several minutes. So you basically, in just a single olivine grain, you basically just locally accumulated iron to form iron metals within the actual the silicate. Same here. So compare what we see on our experiment. So that's what happened to our sample, both in transmission and on the surface, compared to what we found both with our meteorite experiment. So it's an imaging of one of our heating experiments that we did here at U of A, compared to what was observed on Apollo 17 lunar source, showing you that basically the exact same texture that we can form by flash heating the sample. So basically, flash heating is very typical of what you can observe here and what we can even observe on the surface of the moon. In terms of implication, is if we think about circumstellar silicates that are exposed to both high temperature and high energy particle, what those really initial results, so it's really preliminary experiment shows that basically our irradiation experiment are consistent with what we found from TM studies of presolar grains, so in the lab. So when we look at those presolar grain in the lab, they're consistent with both. We found amorphous olivine, so it's typical of what we might accept for amorphization of olivine in high energy environments. So basically, if you think about a supernova, for example, so a stellar explosion, it's very energetic. It can easily, it has a lot of really high energy particle. It can really easily amorphize those silicates. So it's not surprising that a lot of the silicate we have in the presolar grain collection are actually amorphous. And that's why we have a higher abundance of amorphous silicate than crystalline silicate, even in the stellar medium. And then we see that flash heating to 1,000 degrees lead to the formation of iron-nickel nanoparticle, which is not typically observed in those presolar silicate grains, which basically show you that the mineralogy of presolar silicates is mostly reflecting irradiation in the stellar environment rather than flash heating or thermal processing. In terms, just to summarize some of the information I show you today, is basically ion irradiation of San Carlos olivine is consistent with what we expect in circumstellar environment with a higher abundance of amorphous silicates. For the heating of meteoritic material, above 500 degrees, you will see significant change to both the microstructure and elemental composition, such as melting or sintering and formation of iron-nickel particle. Larger and larger iron-nickel particle, the longer and the highest temperature that you keep the sample at. And at temperature above 800 degrees, you lose all the volatiles. So like sulfur is completely lost into the vacuum, and the iron is contributing to those iron-nickel particle, and then graphitization of the amorphous carbon. So I hope I show you in this preliminary data showing you basically that simultaneous electron imaging during in-situ heating, it's inside of both an electron microscope or a transmission electron microscope is really critical in terms of constraining thermal processing and the effect of thermal processing, both on the surface of asteroid, but also inside of asteroid with more long-term, lower temperature heating inside of asteroid to try to constrain what we actually observe from the return sample and compare it to a laboratory experiment, and try to get, as we get more and more heating experiment, try to really match specific temperature to specific microstructural composition that we can see in the sample. One of the first thing that the next step that we are trying to do is to try to compare functional chemistry for organics. So try to see what's actually happening to the organics in terms of functional chemistry. So if we look at organics, it's not just amorphous aromatic carbon. There is a lot of nitrogen, hydrogen. So trying to see what's happening to all those compounds as it's being heated. We know it's getting graphitized, but it's probably a lot more complex than it. So trying to combine it with both EELS, or electron loss spectroscopy, so we can basically compare it as we heat the sample slowly, see what's happening to the sample. And one thing we haven't done yet is looking at what really long-term exposure to low temperature. So if you heat the sample at 200 degrees, instead of just a few minutes, like less than an hour, leaving it for several hours and see what's actually happening to the sample at those lower temperature, which is most likely what will happen on an asteroid, at least in the inside of an asteroid. We'll be happy to answer any question. Thank you so much.
Hey, we have plenty of time for questions. Anya, go ahead.
So you mentioned hydrogen in the end, but then more than organics, like I was thinking like the solar wind implantation of hydrogen. Like, are you thinking of like looking at what happens to that when you have this kind of metamorphism?
So one of the things that we are trying to do, and we are going to do it as soon as we get the nanoSIMS installed, is trying to combine see isotopic variation. So basically trying to understand we know that when you heat a sample, I didn't show you an example, but we see like particle like shrink, and so it's basically likely due to loss of water. So like hydrogen that was trapped in the sample, so you basically shrink dry the phyllosilicate, and you just lose all the water that's trapped into it. But there is very few studies that basically show how like hydrogen isotope will vary with temperature. So one of the things we want to do is try to compare the evolution of hydrogen isotopes as you progressively heat the sample.
Right. And then the other question that I have is, so are you planning to like quantify the loss of these volatiles in a sense? Like for someone like me who thinks of like, whole planets, like if I look at the regolith composition on any planetary body, right, I would be wary of these kinds of alterations affecting, the primitive signature, right? Of
It's
what's a regolith now? So like what kind of warnings, I guess, do you have for people like me?
It's a good question. So that's it's a tricky part for us, because for us we basically lose the volatile in vacuum. So basically blow it in the vacuum,
Right.
or it gets stuck on the chamber, but we don't quantify it.
Okay.
There is ways we have been investigating ways you can actually connect Was I muted?
Can you see? Yeah, there we go. There we go. I think it was unmute. I think that was the problem. So
Is it?
yeah, I think
I don't know what's happening to I don't know where the keynote is.
that's okay. At least people can hear you now. There's your keynote.
Is it?
If you go to desktop, yeah, if you go to the keynote there.
It shows it's playing, but it doesn't show me where it is.
Yeah.
Oh, there you go. I don't know what I did, but it worked.
So at the beginning of the talk, you mentioned about water
Yeah.
being an important role, and I realized it wasn't an experiment you did, but at the same time, you said that all the volatiles get blasted off when you heat them up. So how does the water get there? Is it in the phyllosilicate?
Yeah.
And then how does it react? Is that something that's going on at much lower temperatures?
So there is different ways we think water on asteroids. So but the idea is that water was present initially as ice, and so as the asteroid was heated up due to, for example, radiogenic aluminum-26 decay, you basically melt the ice and you basically have actual liquid water that basically interacted with the asteroid, forming those hydrous minerals like phyllosilicates. So all the water basically on those asteroids is trapped inside of those phyllosilicates. And I didn't show you, but we did some experiment with like Murchison where we see a lot of phyllosilicates. And we are lucky one of the particles we were loading must have been a lot of phyllosilicates. With just EDS, it's difficult to tell. We can't quantify hydrogen, so we can't tell that it's a phyllosilicate for sure. But what we saw, you could say, as soon as we reach like 400 degrees, for example, we shrink completely, showing that it basically just lost probably all the hydrogen.
So is that water like got to now be in the center of the asteroid, not get blasted away?
On the asteroid, it's probably it's just lost in space, my guess. When there is like a impact or like any heating on the surface of the asteroid, that basically just volatilizes, and so it's just lost in vacuum.
So what you sample with the OSIRIS-REx, I mean, you're sampling right at the surface, so down below that might actually be more rich in those. Well,
probably. But that's assuming that the trend will be linear. But yes, we are basically we sampled basically the first 30 centimeters or so, 20 to 30 centimeters of the surface. So most of the material some material on the surface, which is the only way we can collect it.
Okay, other questions? Yeah.
Your iron nickel droplets. Is there any degree of variability in the composite? I mean, more iron, more nickel, and some. Is that grain dependent? Or they homogeneous?
The answer is like, I don't know for sure because we haven't quantified yet. But if you look at one of the EDS map. I don't know why it stopped playing, but I'm gonna manage. I think I understand. There we go. I don't know why it's not. Anyway, if you look here, if you look in detail at the map, you will see that the iron and nickel signal is very different from one particle to one nanoparticle to another. So there is clearly differences in the abundance of iron and nickel in each particle. And it's the same, I would say, for silicon. It's more difficult to quantify silicon because there is silicon everywhere. But definitely, I would say there is compositional differences in terms of abundance of those elements. And that's something we need to constrain. Quantification with the EDS system is tricky because you need to have a standard. So we're trying to find ways to at least get relative abundances as we heat the samples.
Do you roughly see that contrast grain to grain though, or are there outliers? Or?
Mostly you see the larger the particle, the stronger the iron signal is. So I would say so typically, but I don't. We haven't investigated the trend yet to basically confirm it.
More questions?
Yeah.
Sure.
So the time of the heating experiments, you said this is like, you're just kind of guessing right now.
Yeah, those were just first guess.
Is it constrained by anything from theory about the bombardment by by solar wind or anything?
So yeah, so for space weathering or like impact, we know it's very quick. So the shortest flash heating we can do, the better to simulate it. For long-term hydrothermal processes, like lower temperature, it's very long-term. So we're talking about years or hundreds of thousands of years. So in terms of scale, we will never be able to simulate that per se. But the longer we can heat the sample at those low temperatures, I think the better we'll be able to see those more long-term effects that can happen to the samples. So, and there is some constraint in terms of temperature and timing based on mineralogy. So there is modeling of mineralogy in meteorite that basically try to simulate what particular meteorite actually experienced in terms of what temperature regime, for how long it likely must have experienced based on experiment, but we haven't tried to match those because for now it was basically just trying to see if it actually worked.
I've got a question.
Yeah.
I was wondering, so just building off of Ananya's question of maybe measuring the volatiles and quantifying.
Mhm.
And you said that you had plans for potentially linking it to a mass spectrometer.
It would be possible. It's going to be tricky because you have to change the pump system, but it's something that would be cool to do.
Well, how, in general, like how much material of gas do you get?
Very little,
Right.
because we are talking about really tiny amount of particles. So it's going to be very little, but it's going to be tricky. But it would be great if we can. That's the tricky part.
Because on the flip side, you're also, unless you combust everything, all of it, you're going to induce some fractionation there because you're heating so much as well, right? So that, I was just curious from that perspective. And whether, so then what about also, do you have any plans or is it even possible to maybe map out the isotopes of the systematic?
So the idea will be to do, so the plan what we are doing to do is combine it with nanosims. So doing nanosims imaging, so like mapping, for example, carbon, nitrogen, hydrogen isotopes before you heat the sample and then progressively at different temperature and see what's happening to the isotope. So there's very few studies that basically try to combine it with people have tried to do it more in a more rough way of like you can't see what's happening to the sample because you can't monitor the temperature very well and you can't monitor what's actually happening in terms of mineralogy. But combining with the nanosims, I think it will allow us to actually see the spatial variation. So if you look at the sample, when we see all those things happening, even looking at iron isotopes will be very interesting for us.
I have a quick question.
Sure.
So you chose San Carlos olivine, right? So what's the usual like strike number for olivines in these kinds of grains? I'm asking whether like the phosphorite content would have an effect on.
It does.
Okay,
It does.
Okay.
It does, because we see a really broad range. We only choose San Carlos olivine because it's the most straightforward as the initial, but we need to change to do a broad range of them because you can see it even depending on the silicate that you have, and we don't even know if it's crystalline silicate in a meteorite. Depending on the composition, the effect is different. So it definitely does.
Because I guess for more iron-rich olivines, you would expect probably more of those.
And some of the experiment actually showed that those nanoparticles actually formed by the combination with the presence of carbon. So it's basically creating a reducing environment, basically facilitate the formation of the. So it would be interesting to see if you. But we do form it on San Carlos olivine where there is no carbon. So I think that's why I really want to do it a more systematic way, we like list a really well-defined standard material rather than just meteorite.
Guess we have time for one last question, if anyone has it. Okay, if not, can we thank Pierre again?
Thank you.